Hello, I'm Professor Steve Miller. Today I want to talk about the Bradshaw one-equation turbulence model from 1967. Bradshaw and his colleagues developed a one-equation turbulence model, meaning it has one particular partial differential equation to close it with corresponding algebraic enclosure coefficients, which might be, of course, empirical and calibrated against a flow. It's a one-equation model for the turbulent kinetic energy. This particular model is using a boundary layer simplification, which we previously discussed, and it is limited to high Reynolds number flows. In fact, the model neglects the typical molecular viscosity effects within flows like nu. As we know, near the wall of the boundary layer, the viscous effects dominate, and therefore this model is not valid near the particular wall of a high Reynolds number turbulence boundary layer, and therefore we must use wall functions, which are classically used in many types of flows. This is good, of course, because it saves computational expense. But you have to assume something about the form of the turbulent boundary layer and the viscous subregion near the wall, which can affect your entire solution. Also, the model assumes that the turbulent diffusion is determined by the large eddies only. The characteristic velocities are completely determined by the local Reynolds stress, as we'll show in the following equations, which we'll define as tau hat. And this is valid in the region of y over delta, where delta is the boundary layer thickness, between 0.25 and 1. Which is quite a large region of the whole boundary layer thickness. Through this analysis, it can be shown that the energy of the fluctuations correlated with V prime will go and be proportional to tau hat of the square root of tau hat max, which is, of course, local Reynolds stress. And we'll define these equations momentarily. Now this model depends on, of course, the boundary layer equations, which we previously derived, that consist of continuity, right? You have partial u partial x plus partial v partial y is 0. Momentum, which is u partial x plus v partial u partial y equals negative 1 over rho of partial p partial x minus partial y of u prime v prime bar, which is the Reynolds stress. And we'll call these two equations 45 and 46 relative to previous classes. Oh, and we need one more equation for, of course, the turbulent kinetic energy, right? Because it's a one-equation model. So we'll have u of partial k partial x. So k is turbulent kinetic energy plus v. Partial k partial y is d plus p minus epsilon. And of course, we need to define d, which is negative partial y of 1 over rho p prime v prime bar plus 1/2 v prime of u prime squared plus v prime squared plus w prime squared. And this is all correlated. Right, and we also need the production term pk, and that's negative u prime v prime bar times partial u partial y. So of course production only occurs here when we have a partial u partial y not 0 in the boundary layer. And let's name these equations too. I'll just call this as 47, and these two are defined here, so we won't define them. So these are the major equations. And as I already mentioned, this is a high Reynolds number turbulence flow, implies that contributions from molecular velocity appear and are neglected here, and it's not valid near the wall, and we have to use wall functions. And I've already mentioned all this in the major notes. We will define the kinematic Reynolds shear stress. This will be nothing but tau hat equals tau over rho, and of course if you take tau divided by rho, we'll be left with the negative of the component of Reynolds stress. So we can do some dimensional analysis and show some dissipation, and Bradshaw and his colleagues wrote that dissipation will go as tau hat to 3/2 all over L, where L is some characteristic length scale. So of course, epsilon is dissipation. And we just defined tau as the kinetic Reynolds stress. So in the particular one equation model which we're looking at, L will be modeled by an algebraic equation. And in the particular case of production being equal to dissipation, that is pk is equal to dissipation, if we make this assumption, then we can rewrite using 49, 48 in our previous equations a new differential equation, which is negative u prime v prime bar partial u partial y, so that's like a production term, equals tau hat of partial u partial y, which of course is equal to epsilon, which is equal to tau hat 3/2 all over L based on our dimensional analysis, which we showed up here. Cool. And we will call this equation 50. So I think we're at 50 now. Okay, and you can simplify 50 and find equation 51. We've got tau hat equals L squared times partial u partial y squared, which is a very simple differential equation, and that's a very important equation 51. You'll see for the particular case where the length scale is equal to the mixing length scale, we have this case. Now, the turbulence can be assumed to be determined by the largest eddies, which have a length scale L, and these cover the most of the boundary layer, as I noted in our notes up in the beginning, from 0.25 to 1 for y over delta. And therefore, a characteristic velocity of the fluctuations would be totally determined by the local Reynolds stress tau hat. The diffusion would be characterized by the gradients in tau hat, which can be represented by tau max, as I noted before. This means that the maximum value of tau hat in the range of 0.25 for y over delta from 0.25 to 1. We would then be able to model and assume that q squared v prime bar is proportional to tau hat of square root of tau hat max. That's the line of physical thinking in their paper. And of course, I should mention q squared, which I already defined as u prime squared plus v prime squared plus w prime squared. This same particular approximation is also made for the pressure diffusion. And if you follow these steps and look at the details of the paper, but I'll show you the major results, we'll get these particular modeled terms. We'll get p prime v prime bar plus 1/2 q squared v prime bar all over tau hat and square root of tau hat max is equal to a term called g, which we just defined. And we'll also get tau hat over q equals a1. So these two particular equations are 52 and 53. And we'll look at a1, g, and l in a second. These are determined through calibration of particular experiments that Bradshaw and his co-workers looked at. And they proposed empirical closure equations for G, A1, and L. And they wrote L over delta will be some function, which they find, of y over delta. And they found G, and they proposed G goes as the square root of tau hat max all over u squared, where u is the edge velocity or free stream velocity times f2 of y over delta, where f2 is another function. And of course, delta and y would be defined with u of u over u. So u is the actual streamwise velocity, and capital U is the edge velocity, is 0.995, which is a definition people use. f1 and f2 are basically universal shape functions, and they also choose a structure or constant a1. This is a1. Looks more like a q, excuse me. a1. Of 0.15 from my notes. Now, if we take all these model equations here and 52, 51 and put it into our previous equations developed, you can show and find that we find the particular one equation model. Once again, we'll have continuity, partial x partial u partial x plus partial v partial y equals 0. This is the D'Alembert condition. We'll have a momentum equation once again, u partial x plus v partial u partial y equals -1 over rho partial p partial x plus partial tau hat partial y. So there's our momentum equation. And then we need our TKE tracking type equation. We'll have u partial x of tau hat over 2a1 plus v of partial y of tau hat, that's a hat, sorry, all over 2a1 equals d plus p minus epsilon, which we defined before. So we'll call these three major equations, of course, 54 for continuity, 55 for momentum, and 56 for our TKA simple one equation model with the particular closure coefficients and functions which we previously defined. The full functional forms, F1, F2, are really built in here. And what is d, p, and epsilon? Well, d, through these simplifications, will be negative partial y of g tau hat square root of tau hat max. And then we have p, I believe, equals tau hat of partial u partial y. And final term for closure is epsilon equals tau hat 3/2 all over, you guessed it, L. It can be nothing but L, length scale for dimensional considerations. This is the final form, these three equations for a fully high Reynolds number turbulent boundary layer with wall functions of Bradshaw and colleagues from 1967. Thanks for your time today. I'm Professor Steve Miller.